Control. B. Group B. All right, usually we only give it to one or two groups the first week because you get better each time. And look at you, you are on a roll. Yeah. Let's go, group A and C next time. Okay. All right, so we have our gas chromatography lecture start today. We have Dr. Gary Reinexis. He's been helping me teach this part for 17 years at least, right? And before then, you were teaching for the analysis the entire
Could
time.
have been. It's been a long time.
Yeah, and he will be teaching MS, and this is his analytical passion, GC and MS, and we usually argue which is better, GC or HPLC.
Oh, that's clear.
That's clear.
There's no argument as far as I can see. Oh,
Yeah.
absolutely.
Long,
You may differ, but
yeah, long history of research using GC and MS, especially flavor research. So, well, it's all yours.
thank you. Well, yep, that's the topic. These are some of the things we're gonna go through, talk about naming, talk about hardware, a little bit about how we do separations and how we do them the best we can. We'll throw in some problems in there, basically conflicts, things that don't work right or have gone wrong. So then also some applications. So that's kind of going to be the program we do. From a history standpoint, this was kind of chromatography really started, I guess, with the separation of dyes. So colors by a professor quite a long time ago. So chromatography's been around for a bit. Kind of went towards foods when Svet, S-W-E-T-T, talked about or looked at separation of plant pigments. I get really interested around 1941, and that's really the first theoretical development of gas chromatography. So chromatography before that time was done in beakers and columns and all kinds of things. But now we're starting to build an instrument based on chromatography to do the separation of volatile compounds primarily. And so the first gas chromatograph was really put into or created in 1952. 1954 is kind of the first time that they really were a system that worked. At one point, they were putting things into the instrument. It was coming out as a gas, and they would collect the gas and titrate it, and someplace else and see about acidity and so on. We don't have to do that anymore. It's really gotten to very sophisticated, nice, complete systems. You inject in one end, you get results out on the other end, and so it's really come a long ways, obviously. It is relevant that gas chromatography is a mature technique, more than 30 years ago. By mature, I mean there's not going to be any more improvement in terms of, we're doing separations. We've reached the theoretical maximums in terms of performance. And so what was working 30 years ago is probably as good as what's working today in terms of sensitivity. That's it. And so that's good in some cases, meaning if you've got an older instrument, you're perfectly fine. You don't have to be buying a new a new instrument every 5 years or 10 years. And when you walk down to our labs, well, we're fairly modern, but we're certainly not, it isn't yesterday we bought them. These things end up being rather expensive. So we're pretty happy that they've kind of reached that maturity and we're there. So we're in that group. These are a few of the components that are measured by gas chromatography. I think these are all related to foods, and I could actually fill a couple more pages. It really has broad application in terms of food analysis. So kind of some of the examples. My interest was flavor. Flavor not from a taste standpoint, but flavor more from an aroma standpoint. And so there's nothing better. Aroma compounds are volatile. You smell them. This is a method of separating volatile compounds. So it is obviously my research home. what is the process? Basically, you get a sample. We'll spend some time preparing samples. The biggest challenge today is how to prepare the sample to feed the gas chromatograph, to feed the instrument. That's our limitation. So we'll, like I say, we'll spend some time with how we get samples into this instrument. We can't just open up the cap and put a donut in or something. We've got to do an isolation. So we've got the volatile compounds that we then separate here. And so the sample is vaporized. So typically is a liquid in some form in a syringe. We've done an extract. We've put it into a hot injection port where you will see this, where the sample kind of goes poof, gets volatilized, and then it gets swept into a column. And that column is up to 50 meters long. So it can be a very short column, or it can be something like even 50 meters long. It's a heck of a long column if you think about it. There aren't any other techniques used in our lab where they could stretch it down the hallway and say, hey, I'm doing my work. So it's interesting in that sense. And as these compounds, these mixtures of things we put in, they flow through that column, they interact with the coating on the inside of that column. And some of the chemicals in there, some of the components, they really like that coating on the inside of the column, so they slow down. Those that really don't care for that coating keeps on moving with the gas, carrier gas, the mobile phase. And so we just basically the separation in time of what elutes out of a given column. So that then we, of course, put a detector on the end. Said one time that we had to collect whatever came out of the column and do titration or something. No, we've made really good advances in detectors for it too. Probably the most powerful detector by far is mass spectrometry. And I'll spend some time with that as well. So we'll talk about gas chromatography, I will, and we'll talk about mass spectrometry as well. They're just a kind of a combination made in someplace in heaven, believe me. And so this is really a simple diagram of the system. And so we're going to enlarge upon these and give you obviously much more detail. We need a mobile phase. In any type of chromatography, we need a stationary phase. We need a mobile phase. So here's our mobile phase, and there's flow controller. And it's coming in here. We have to have some way to introduce our sample into this flowing gas, the mobile phase. And so there's sample introduction. Most commonly, that's done with a syringe, a very small syringe, probably 1 to 10 microliters. And so we'll go ahead and make our injection here into the gas, and then we look at our separation here. How each of the analytes interact with this coating, and they come out and they have to be detected in some way. And again, we'll spend time with kind of each of these parts. We'll talk about the injection port, we'll talk about the column, we'll talk about the detector, and then of course, the kind of the data analysis, what we get out of it. I'll give a little more detail in each of these parts because it's important. It's really important to know what you're doing. I hate to see somebody come into an instrument, they don't have the funniest idea what it does. Make an injection, get something out of it and think, oh, this is good. I really like to say, this is what we put in, this is what happened, how it happened, and here's what I got from it. So I hope not bore you with some of the detail. Detail and understanding the instrument is really important. And so this is a little more detailed, figure than the last one. So I said last time we have a tank of carrier gas, your mobile phase, to come in and go through the column. But we need a detector out here, as I said. And this is actually a flame. That's what, if you can see that little image right there. So what happens is we go ahead and make our injection, we get our separation, and hopefully each component comes out separately. It gets flamed, burned, essentially, in a flame out here. And right above that flame is the detector detects ions. So basically, we're burning everything that comes out of it, and we're just simply counting the number of ions that it's burned into. The more compound, more ions, more electrical current you get out of it. So, like I say, fairly easy or fairly still system yet. So kind of look at the gases. We'll go through those parts of it. The gases that we have, they do serve, like I say, as a mobile phase. They are high purity, most commonly. Well, I about say most commonly historically. We've used helium as that gas that's flowing through the column. It's going to move things along. Helium exceedingly inert. Nothing happens to it. It's a nice gas. We can also use hydrogen. Hydrogen, great purity. You'd say, gosh, that's kind of reactive, but it's not reactive under the environment that we use it. So I don't worry about reducing something, changing the chemistry because we got hydrogen in the environment. And see, historically, we've used helium, but today we use almost exclusively hydrogen. And the reason for that is the price of helium's gone crazy. You'll pay $1,000 a tank or something like this, and and it won't last forever. And so we've kind of gotten rid of the helium just out of cost. And we've substituted with hydrogen, which isn't a bad substitution. It's actually a pretty good substitution. We've done this before simply because of cost, and it doesn't hurt us at all. It probably helps us a little bit in separation. So helium, no more. Hydrogen is this made up now of that mobile phase that's going through the system. So we need to get our separation, of course, and then we got to somehow detect what comes out of the column. So got the column, we're going to be eluting compounds, hopefully one by one separately. They go into the detector and they get detected. That's a kind of obvious one, isn't it? But we have many different types of detectors. And we'll just do a kind of a quick interview to each of those or review of them. So different detectors, mass spectrometry, thermal conductivity, and so on. They each have maybe a slightly different need in terms of a carrier gas, so going through the column. But for us, the flame ionization is most common, and you'll see that again coming up. And so, good, we're happy with hydrogen, no problems at all. Our other common detector is actually a mass spectrometer. So we elute something out here, we burn some, we count some ions. So what? Hey, guess what? We got some ions. Where'd the ions come from? What did we just burn? And that's where the mass spectrometer is really nice to add on. So if we just have a gas chromatograph and flame ionization, we just get a peek on a piece of paper and we don't necessarily know what it is. What we do is, of course, try to put standards so no one's in there. Oh, look, this elutes the same time. It's probably what we're looking for. I'm much happier having a mass spectrometer on the end of it because then it blows the, whatever comes out, the detector gets blown up and you look at all the fragments and you can say the fragments, oh, that's what it is. So this flame ionization is good, but I really do like mass spectrometry as being a more flexible choice, a better choice for us. Since we have this gas, this carrier gas going through the system, or hydrogen, kind of look at what we need to do with that. We certainly have to have some kind of regulator, flow regulator. We want to control how fast the gas is going through that system. And so that control of your mobile phase, how fast is that going, is important to us. And so we have good flow regulators, pressure regulators, and you can probably go down to the welding shop and you can get yourself a regulator, but it isn't what we need. We need some high quality ones. By high quality, I mean those that don't, when they get hot, they don't give up garbage. And so we basically use specialized flow controllers. They look the same, and sometimes you'll come into the lab and I'll say, wait a minute, that's a welding. That should be down at the shop. That should be here. Anyway, don't ever forget that if you end up running here, keep an eye on it. They are really sensitive precision instruments, they're just regulators. So again, not only are they much more inert and clean, they're also much more precise and reproducible. And the parts are all stainless steel. They are high quality machined regulators. So again, if you're doing the business, kind of keep track. keep track of that. So that's our kind of flow system coming in. Where does that flow go? It goes from this tank of gas, gets controlled. It goes into our injection port. And as that suggests, it's where we inject our sample. Okay. And this is a diagram here of that system. What's the purpose of this injection port? Well, it serves multiple purposes. Probably the first one is it's how we get this sample into this pressurized gas. So there's our carrier gas coming in under pressure. We can't open the lid and pour a sample in. We've got to take that syringe and inject it in here. So we put the syringe in here, push it down. And this is hot. This may be 200 degrees centigrade. And so when we push the plunger down, our sample goes in, it goes poof. And that's very important to us, it's quick volatilization. And so that's basically a way to introduce the sample into our gas that's under pressure. It vaporizes our sample, so it puts all of the compounds into a gas phase so it can move along with this carrier gas that's in. And actually, so most often, it's also to reduce the concentration of our analytes. That may sound a little weird. Why do we want to reduce the concentration? You'd think we want to boost it, but very commonly, we have enough sample that we can't measure it very, very well. It's maybe it's a different way to put it. If I have a solution, I have 1 or 2 microliters of liquid that I put into a syringe, put in here. I can't put that much liquid into my system. I can measure it. Oh, I can measure 1, 2 microliters very accurately. I go poof, but I measured accurately, but it's too much. So it permits me to use bigger samples. Does that help? Would that make more sense? I can use a regular syringe. I can accurately measure it, and then I get rid of most of it because it's too much for our system. So hopefully that came through. So here's our gas coming in. A little bit of it goes out just on the side here to kind of keep things clean. Then the majority of our sample goes down here, and that's where we get a splitting occurring down here. And so that, like I say, that gets rid of probably 90% of our sample or more. And then the other 10% goes into the detector. Yeah.
With the purge, what is the purge gas? I saw all these diagrams. What is getting purged with this?
Okay.
I understand to clean it up, but where is that going?
Good for my neck. Okay. So here's our carrier gas, our bubble phase coming in under pressure. We make an injection, and some small amount of this will actually be flowing out and going on its merry way. The purge gas is up there simply to keep this clean up here.
Mm-hmm.
And that's
I was just wondering where it's
Yeah.
in and out.
So that's maybe 2 mils per minute. We may be taking 30 mils in or 40 mils per minute of gas. But about 2 of them just kind of keep on going across there to keep everything clean. Because this is a rubber polymer.
Mhm.
Well, it's not a cheap rubber, it's a synthetic material. And so, but that's going to be 200 centigrade, 250 centigrade. It's going to give up volatiles. I don't want those volatiles going in my system. So like I say, that just kind of keeps this place clean up here. Okay. So that's kind of where we put our sample in. We put them into what we call our injection port. And like I say, it's easy to measure 2 microliters or 1 or 2. So we use a big sample and we get rid of most of it. So easy to measure, but we'll get rid of it. And so that's what we call the injection port. Can be different kinds to suit different functions. Most commonly, we use what we call a split injection port. And like I say, only a small part of our injection is really going to be going down the column. Yeah.
For the purge gas, is that also hydrogen gas?
Yep. And one of the, I have a strange sense of humor sometimes, but one of the funny things to me is I probably have gotten 20 phone calls from people that were do gas chromatography around the university and elsewhere. I said, Carrie, we can't get helium anymore. It's really expensive. some people are using hydrogen, but hydrogen is flammable. It's going to explode. Yeah, maybe, but I don't say maybe, but I'm oftentimes inclined to my sense of humor is a little strange. But the idea that these gases are in small quantities, they're very controlled where they go, but they're not going to catch on fire. There's no, we actually have trouble keeping them lit. That if that makes sense, to have a hydrogen flame and a hydrogen burning, it takes exactly the right proportion of the hydrogen gas and air. And so it's not going to happen by chance. You have to work at it. So we don't worry about flames, fires, or explosions.
You got bigger
But-
problems if you
But
do.
people call about that. I said, oh, by the way, hydrogen is probably 1,000th the cost of helium. Well, why else do we want to use hydrogen? Yeah, cheap. So what different types of injection ports do we have? Well, I've been talking about a splitless one. I'm sorry, a split one. So we split out most of our sample. There is a splitless, and I think we'll get to showing that in diagrams. But in that case, whatever we put in goes to the column. And we use that only when we really need sensitivity. We can't afford to throw anything out. Then we'll do splitless. We really prefer split, nice, clean, quick, and so on. This we will do only if we have to. So there are some cases we need the sensitivity. We can actually, instead of having that injection port sitting at 200 degrees centigrade and injecting into that really hot environment, we can inject into a cold environment. Cold, I mean room temperature. So there may be situations where our compounds are heat sensitive. And so then we use a slightly different way, get rid of that 200, 250 degrees centigrade and use instead an on-column injector. In that case, we probably have a slide coming up on that, but we have the syringe that has a needle about that long. So we just kind of draw our sample up in it, put it down in, put it down in, put it down. So it's in the column. It bypasses everything that's happening up the injection port. It goes in the column. And that's cold. You know, cold meaning, well, oftentimes start off about 50 centigrade and program up to 200 centigrade. So it's cold in comparison to what we'd otherwise inject into it. So if our material is really heat sensitive, we get rid of that big heat shock initially. Program temperature, in that case, maybe we inject into something that's a little above ambient, and we can then control the temperature of that injection port. So there's different versions on these things. Actually, in some cases, we got large volume, we can inject a milliliter, not a microliter, but 1,000 times that. So there's a lot of opportunity to do different things in the injection port. Depends upon your sample. So when you're reading a procedure, you know, they may be talking about different methodologies. By far, this is number one. I would say 95, 99% maybe of all work is done with this type of a system, a split injection port. And then this remaining goes in this direction. So that's number one in terms of how we do gas chromatography in most cases. We kind of take another diagram going a little bit further up this line. We have now, here's our injection port here. We got our column sticking up into here. So our column comes right about there. And here's our sample gas coming down, and our gas goes away. It's the vast majority. Our flow through that column is only about 1 mil per minute. I'd say that's a very, very fine column. And so basically then this goes on to the detector. And these kind of give you an idea of flows. We have about 3 mils per minute coming across here to keep this clean. We have something like 50 mils per minute coming down here. One portion goes this direction, but only 1 mil per minute goes out for analysis to get to the detector. So you can see these parts, again, controlling where the gases are, where the gas flows tend to go. That's in a split injection. So in that case, most of what we inject actually goes out here into the room. Only a small amount goes this direction. But there are other types of injection where we'll put more of the injection onto the column. So we can take a look at that in this one. So this is where we have what we call a split less. And so in that case, we're going to be feeding most of what comes from here into this column one way or another. So basically, the only thing to keep in mind here, split, okay, that works well, handy for most times. But if you got something you really, really need sensitivity, then you don't want to split, put 49 parts out the the garbage and one part into the instrument. You want to get most of it into the instrument. So again, there are simply ways that they manage getting more of that into the detector itself or into the column itself. This is the on-column one where we really don't want to heat the sample. Here's where we have this very, very long syringe. So this is kind of the top of your injection port. Your injection port's down here, your column is over here, and so on. But this is just a kind of a silicone stopper that we can actually take a long, long needle. It may be 20 centimeters in length. We just kind of feed it down till we get to the column. And that's warm, but not overly hot. So if something that's going to thermally degrade, okay, we've got a way to deal with it. And so, our vast majority of samples are run kind of standard split injection. But these things about split list and on column, they're just kind of niches where we got something that's really, really sensitive. It's rather unique. So say 99% will be taken up just by this first one I showed you about split injection. So that's how we kind of get sample into the gas chromatograph. We need to get into the column so we get our separation. There we now use capillary columns. So they're very, very small diameter columns. And so we have two types of capillary columns. One's kind of what you call open tubular, and the other's a porous layer open tubular. Again, kind of something minor I won't lay awake worrying about. But the open tubular is just this glass, very, very fine glass that's got a thin coating of a film on the inside through the whole thing. But the porous layer open tubular, it's a thick film. So this is a much thicker coating. So you have a thin film or a thick film, thin or thick, either one. And again, there can be extra separation taking place with the coating. So again, specialty, not common, but it generally is used. I should have brought a column with me. They're rather interesting. They are glass, and I can tie knots in them. You think, really? You're going to take that glass and you're going to tie? Sure. Want to see? It's exceedingly strong material. And it's the thin layers make it very flexible. It's such a thin material, a strong material, you can bend the glass. And normally we bend the glass into kind of a holder of something like this. So you may put 20 meters of this on the spool and put it in an oven, and that's our gas chromatography column. Generally, the columns are fused silica. They're extremely strong glass. It's a fused silica material. The diameters may be 0.1 millimeter on the tiny side. You think about it, up to 0.53 millimeters. So a fairly broad range. I mean, that's a factor of 5 in terms of bigger or smaller. And we tend to work on the smaller range. The smaller the column, the better our separation. If we've got a big column, we get different flow through the column. Maybe the center on a big column, center gas goes a little faster. Oops, I'm separating some analytes. They're going away. Some are trailing behind. So we really want small diameter columns to get our good separation. They can be up to 60 meters long. So how's that? We can sort of stretch them down the hallways here for 60 meters. And that gets rolled up into this nice little coil that sits inside of your oven. We don't tend to use 60-meter columns very often. Why? They're generally not needed. It's only when you have one heck of a problem do you start reaching out for that kind of length. This is the workhorse, basically, a 30-meter. It's still pretty darn long when you think about it, but that's our workhorse. And so we've got our fused silica glass, extremely strong, thin film put on the inside of it, this film coating. And again, that coating can be very, very thin, 1.1 micron to up to 5 microns, and 0.25 is normal. So our normal is a 0.25 millimeter inside diameter, 30-meter length, and a coating on the inside to get our separation of 0.25. So that's the workhorse when it comes right down to it. So what is that coating that's put inside the column? That's what gives us our separation primarily. And so these are the common coatings that go inside of that. There's what, 1, 2, 3, 4, 5, about 10, 11, 12, whatever it is, coatings that we've got over here. It's a composition. And so these are the materials that we put inside. If you're going to be having a mixture of compounds, you want to separate, you want to measure mixture of compounds that are very non-polar. You want a non-polar phase inside that glass to get some interaction. If you have a very polar coating in non-polar compounds, who gives a rep? It's going to go right through. So you kind of look at this. Do I want separate polar compounds, non-polar columns, someplace in between? And that dictates then which of these coatings you put inside of that material. And this kind of gives you an example of what types of compounds would you use this non-polar column for. Over this direction tells you what they are. And if you go to the catalog, okay, this is called an OV1. That's it. I have no idea what OV stands for. How's that? But anyway, it's a very non-polar material. And SE30 is a non-polar. So be kind of used to it. These are very non-polar materials. These designations are getting polar. This is very polar. This is our workhorse in most of the time, is that carbox column. So most of our GCs are set up with them. They're really quite good to look at polar compounds, slightly non-polar. So that tends to be our workhorse down here. How do we know what column to use? Okay, we've got a number of sample coatings back there. How do we know what to use? Well, different ways to look at that. There's something called a Kovacs indice. Kovacs is a professor in Switzerland. And so he came up with some idea that we need to be able to kind of designate how an analyte is going to go through a column, and what kind of column do we need to separate this group of analytes. Polar column, they bipolar, non-polar. So if we have a non-polar column, what kind of coating do we need? And so we basically have linear retention indices or Kovacs indices published. And so I can go into PubMed or whatever. You can just really go online and say a Kovacs index for some compound, and it'll actually spit out the reference that said you should use this coating for that. And they also tend to be published. And so someone in Switzerland or Germany or South Africa, or wherever you happen to be, that compound, that value is going to be valid there as well as every other place. And so if you want to look at some work somebody else has done somewhere, I've got this retention indice saying if I use this column under this condition, it's going to come here. Okay, that's really, really useful to us. My bag tends to be flavor. That's what I'm most interested in, flavor compounds. It's fairly common that I'll get 100 different peaks, 100 different compounds, and they will all come out to, some kind of a shape or form and draw, a line on a piece of paper. Okay, how do we convert that to a known compound? One way is to look at we have a published value. It says that compound will come off at this point, at this time. So it's really useful to us in terms of identification of compounds, understanding what we want to do. So these published linear retention indices are exceedingly useful. Journal articles. Every time someone publishes a paper using gas chromatography, they'll tell you what column they used. Yep. And so journal articles are useful to you. Somebody else probably did the separation at some time. So used to look through literature. And of course, if you're in a company, somebody else probably did this too, or would have done this. So kind of look internally. Do we have any history working with this type of compound in gas chromatography? Has anybody published anything on it ever in any kind of indexes, public indexes? Are they characterized? And so there's a number of ways you know what kind of phase to use, what kind of a separation to expect. There is a, if you don't get anywhere here, which you really will, you should. It kind of goes down to intuition. If you know what you're looking for, well, is it a polar compound? Is it non-polar? If you know what the compound is, you can look up its polarity. And you say, oh, it's a polar compound. Oh, I'll use a polar phase. Oh, it's a non-polar. I'll use a non-polar phase. So anyway, intuition also tends to work, or maybe call it common sense. It'd be a different way to put it. If you have absolutely no idea, and there are times when we don't have any idea what a compound is if we haven't identified it yet. And so in some cases, we just actually take a non-polar column. They're extremely durable, and we put our sample in it and hope like heck we get separation. How's that? So the idea, just go with a non-polar column, mainly because you can go 250, 300 degrees centigrade. So if it's hot enough, it's probably going to elute. It's probably going to get out of there, and they'll probably measure it. And so the idea, work with a non-polar column first. If we don't get the separation, then let's change it to something polar and a polar column and try that. We have different methods of chromatography that show up as well. So adsorption chromatography. So we get an adsorption between an analyte and that column coating. It can be a molecular exclusion. So now we're talking about size of molecules. We can separate molecules by their size in gas chromatography. So we can also do partitioning. Does our analyte partition into your liquid phase? It also can look at vapor pressure or volatility. So when we start doing chromatography, we can take advantage of exclusion, partitioning, vapor pressure, boiling point, a number of different parameters that go into determining whether this compound makes it through this column and is measurable. These are trade names, product names for our different column phases. A non-polar column, we typically would use a DB1. There are other names for it, but DB1. Semipolar, DB5. Polar is carbowax, but there's a new version of that. And it's a little frustrating that each company, each supplier that makes these things, they call them their own name. They may stay with the same numbers. It may be an SE50, a DB50, it may be something else 50, but they kind of put their own name in front of it. And so if they're using it and you don't have it, you don't necessarily feel comfortable about using a different number, but it works. We do usually use heat, so that column actually goes in an oven. Okay, and we take advantage of the boiling point in terms of getting our separation. Things that are compounds that are very, very volatile, fine, they'll come out through the column at very low temperatures. But some of these things may have a boiling point of 200 degrees centigrade. They're not going to go through that column unless you heat that column. So move it, heat it up, so it'll actually become a gas. It can move along with your analyte, with your carrier gas. And most of our ovens, so our column sits in this oven, I can control it from -60 centigrade to 400 centigrade. And so we've got a broad range. For the most part, running from anywhere from 50 to 250 does it. That takes care of really 99.9% of the things you do. But the machine is set up to have a very broad range in temperature if it's needed for some kind of a separation. Well, okay, so we got some way to put our sample into this pressurized gas that's going through a column. We have some way to separate, and that's in the column. Well, now things gonna elute. Now you gotta detect them. And so we need a detector on the end of this. So what's coming out? And basically, what the signal we kind of get is something like this. Here's time, so we make our injection here. How many seconds later? It could be a minute. Well, this is a minute 1.4 minutes. Look, there comes one analyte. Oh, here's our big solvent. Okay, that isn't much interest to it. Here's one analyte, another one, and so on. So we get a chart of basically what's eluting as a function of time. So coming out of that column. And so we have to have some means of detecting compounds. There are, again, many different kinds of detectors that go on the ends. That column can go into many different types of detectors. And they really vary in sensitivity and selectivity. Sensitivity, as you might guess, is really, really an important one because we're talking about micrograms, nanograms, picograms of material that might be eluting out of that column. So you need sensitivity. Sometimes you'd like to have a selective detector that only detects what you're interested in. So again, there's a number of different detectors that are used. We have workhorses, and of course we'll cover workhorses here. So discuss, yep. This is one of the first detectors that was ever used. What the detector basically has is it has this mobile phase gas going through really a heated system here. And what we get is we get a little bit of electrical current coming through here through the system. As if we, okay, that's kind of our base, some kind of electrical flow between the column and your detector. But if we get some analytes in there, so this is something, an analyte of one kind or another, it changes your ability to transfer electricity across to this detector. And so it's called the thermal conductivity because this actually carries heat. So this is heated. This will tend to cool that. And so how much it cools depends upon composition of the gas. So if it's just carrier gas, we get a certain amount of cooling of this filament here. If we have some other compounds in, it'll cool differently. I don't know, I hope that made sense to you. It's fairly straightforward. It's a simple detector. How much does your column effluent cool that filament or that rod? And so it's one of the oldest of it. What are the characteristics of this thermal conductivity? Specificity. What does it measure? Almost everything is different in terms of its ability to transfer heat. So it's called the universal detector. No matter what compound you've got coming out with that mobile phase, with that gas, if there's a material in there, it will change heat. And so it's sensitive to anything. If you get nitrogen, somebody injects nitrogen, guess what? It says, no, okay, I got a peak. It's different than helium, different than hydrogen. So it doesn't matter whether it's a very complicated organic molecule or a very simple molecule. It's going to change cooling. It's going to give you a signal. And that sounds nice, not having specificity, and it does have some advantage. We oftentimes use it for gas packaging. Somebody's gas packaging a food product. They maybe put a nitrogen environment, have an inert. Is it really inert? How did the packaging work? Did it keep it inert? And so we can take a bag of potato chips, stab it with a syringe, drop some gas, put it into this, and basically we get some separation. Ultimately, we have some air in there that kind of changes the heat flow. Maybe I want to detect water. Maybe I'm measuring moisture content of something. And so, okay, water, that will come through my column. It'll change the transfer of heat. So it's a universal detector. It will detect everything except the carrier gas. So that's a standard. And so sensitivity, we're 10 to the minus 7 grams per second coming through the column. 10 to the minus 7th grams, that's not a lot. So it's halfway decent in terms of sensitivity. I say it's poor it is poor in comparison to everything else we do. How's that? So it's darn good, but it's poorer than all of the other techniques we use. The beautiful thing is it's universal. It detects anything. When we start getting these things that are really, really sensitive, okay, they're specific and they only detect some things. So it's an interesting one. Dynamic range, the concentration of what you inject can vary by what, 10,000, 10 to the fourth, and you'll still get a linear response. And that's actually poor because you really want to have a linear response. If you're measuring something, you want to have a linear relationship. So 10/4 is poor, good enough for many of our purposes, but you'll see some of these other detectors that are much, much better. So we have probably 4 or 5 different detectors that are really, really common to us. The flame ionization is the most common detector that we use. We look at this. Here, our column is coming up here. So the column is up there. All the analytes, the carrier gas, mobile phase coming up here. We have hydrogen coming in here. We have air coming in someplace else along this line. Oh, here we go. Here's air. Air comes in, hydrogen comes in. Here's our column effluent coming in. So whatever comes out of the column dumps into here. And we have a flame up here. So we light this. We got a flame inside the system. And so that flame burns all of your compounds and changes the environment up here. And so by the changing environment, basically electrical conductivity, we can go ahead and get really good sensitivity. So we went from 10 to the minus 4 grams per second, 10 to the minus 12 grams per second. 10 to the 12 grams, that's not something you're going to carry around in a bucket. It's pretty darn good sensitivity if you think about it. And that's sensitive to most organic compounds. So it's pretty broad. It doesn't do water. It doesn't do air. It maybe doesn't do a few things, but for the most part, it's pretty darn general. So darn good sensitivity coming up here to the minus 12 grams per second coming out of the column. And I can say good in that sense. Linear range. So our last detector was what, linear to 10 to the fourth or something. Here, our concentration coming out can vary by 10 to the 6th to 10 to the 7th, and it's still linear. So I'm getting a linear response. This doesn't necessarily, chromatography doesn't tell us what something is, it tells us how much of something. And if you got a linear response, you're ahead of the game. You got a nonlinear response, it gets tougher to kind of manage how much is present. And so it's really a workhorse. You'll find every gas chromatograph we have, I think, in the building has that detector on it. It's just so common, so universal. This is a detector that's still used in some cases, maybe used more for pesticides, where we get some other molecules, halogens, and so we want to measure halogens in a system. Can be this detector. What we have here is, here's our column coming up. So anything that flows out of this column comes up. Little bit of makeup gas to make a little more volume coming up here. This is a radioactive sensor, right? Not a sensor. It's a radioactive rod that comes down. And so our analytes come up and go past this radioactive rod. So your radioactive rod's giving off radioactivity, which gets absorbed by any compounds that we just elute out of the column. So we kind of, as everything is going along standard, there's a certain amount of electrical flow between these two. So ions being transferred. As things elute up in here, that changes your absorption. These compounds absorb now, and the wall doesn't get as much. So again, it's very specific. It only works for compounds that like to absorb these radioactivity. Very sensitive to halogens. And that's a real common specific use. If you're working with a compound that's got a halogen in it, chlorine, for example, okay, it's absolutely wonderful on those lines. Very specific, very sensitive. We're down to 10 to the minus 14, I should say 5 times 10 to the minus 14 grams per second. That's a small amount of compound. And that's kind of our threshold. So tremendous sensitivity, not so good linearity. But again, that's sensitivity. So pesticides, herbicides found in agriculture, found in foods, whatever. This is their workhorse for them. But, so it's a good detector, very specific detector, not quite as linear as you'd like. There are a couple other detectors, and we won't say a great deal about them. And so this type of detector actually has a reagent gas coming here. It has your capillary column gas, so whatever coming out of your column here, mixes with a reagent gas and gives off a flame, gives off a color, which is kind of what it does. It looks for chemiluminescence of compounds. So again, very sensitive material, very sensitive column, and it's used in sulfur compounds, very specific. So again, some special chemicals, compounds, works very nice for. Not a general workhorse, but again, certain specific applications. When did we quit? Close to now?
Just now.
We got the gatekeeper there. Okay. Okay, well, we'll pick this up next time. And we'll do this.
Thanks, Gary.
Mhm.